In this video, we're going to see a new way to think about the function logarithm of x. Logarithm of x is a function you may likely have seen in your past in, for example, differential calculus courses, but in this video, we're going to define the logarithm as a particular type of integral, a particular accumulation function. We're going to see that this sort of strange new approach actually has some really nice features, and we can recover many of the normal properties of the logarithm. So let's begin by looking at the old way of doing it, which began not by studying the logarithm, but by studying the exponential function. You know the value of the special number e, and we'll talk a little bit more about e later on in the video. Then e to the x is something that hopefully you can understand. For example, e cubed would be e times e times e. Indeed, the exponential function is something that I can go ahead and graph. And when I graph it, it has some really nice properties. For example, this is an increasing function. It gets bigger as you go to the right. And what that means is that for any output, any y value, there is exactly one corresponding input, corresponding x value. That is, this is a so-called one-to-one function. And what is nice about one-to-one functions is that you can invert them. And indeed, that's what the logarithm was. The logarithm of x was defined to be the inverse function to the exponential. What do I mean by that? Well, an inverse function is going to reflect over the line y equal to x. So if I plot here the line y equal to x, then logarithm of x is what appears on the bottom. That is the reflection around the line y equal to x. That is the inverse function to the exponential function. So this approach is effectively taking the exponential function as the thing we understand, and then defining the logarithm from that. This point about inverses can be stated in a different way. Its definition may be that, for example, the composition of the exponential with the logarithm, or the logarithm composed with the exponential, that either way you may compose these functions, you just get x. You just get the identity function. This means the same thing as my picture of reflecting over the line y equal to x. Okay, so that was the old way of defining the logarithm, where you began with understanding the exponential function and you define the logarithm from that. But now I'm going to introduce a new way of thinking about it. Here's my definition. I'm going to define the logarithm of x, sometimes pronounced ln of x or ln of x, as the integral from 1 up to x of some integrand 1 over t dt. This is a definition that applies for values of x greater than 0. Now, you may have seen this formula written down, for instance, in Calculus 1, but at that time, this equation represented a property of the logarithm function that you'd studied before. Indeed, if you took the derivative of the logarithm function by the definition of the derivative, the limit definition of the derivative, then you could recover that an antiderivative of 1 over x was logarithm of x. But now I'm saying this is the definition. This is what I'm defining logarithm of x to be. For example, if this is the graph of 1 over x, then logarithm of x is just going to look like this. Okay, how do I interpret? Well, let me first begin at this point logarithm of the value of 1, which is just an integral from 1 up to 1. The integral from 1 up to 1 is just going to be 0 by definition. So indeed, the logarithm function at the value of 1 is just 0. Then, let me suppose I take a value of x that's to the right of this point 1. So what I'm doing here is I'm doing an integral from 1 up to x. So if x is to the right of 1, it's the area under the curve of that function 1 over x. This is some positive result, and so logarithm is some positive result. If my x is bigger, then I have more area under the curve and I get a larger value of logarithm. Similarly, let me now imagine that my x is actually less than the value of 1. It's still positive, it's bigger than 0, but it's less than 1. Well, in that case, an integral from 1 up to x, where x is less than 1, is read from right to left. It introduces, therefore, a negative sign. When you have the smaller value on the top, that introduces a negative value in my definition of integration. So in this case, the area underneath the curve of 1 over x from 1 to the value of x is a negative value. And indeed, if I make my x closer and closer to 0, I get a larger and larger negative value for the logarithm. So we have this nice property that as the value of x is getting closer to 0 from the right, then the logarithm is going to become more and more negative. So from this definition, the graph of logarithm is something we can understand. I'll also note that I really like this definition because it's something that we can do approximations for. If you want to know what logarithm of 72 is, for instance, well, it's the integral from 1 up to 72 of 1 over t dt. And because integration can be well approximated numerically, indeed even the definition of integration was sort of a limit of approximations, and so as a result, there is a nice way to numerically approximate the logarithm of any value using this particular definition. Now, one of the nicest features of defining the logarithm this way is that we can use the fundamental theorem of calculus. So let me look what that says. The fundamental theorem of calculus says that the derivative, with respect to x, of an accumulation function is an integral from a up to x, where a is some number, of f of t dt. There's a t here in the x, the t in the integrand is just a dummy variable, and it ranges between the values of a and x. And what the fundamental theorem of calculus said is that the derivative of the accumulation function is just the function f evaluated at x. So now I can take the derivative of logarithm. If I do that, if I take the derivative of both sides, then by the fundamental theorem of calculus, the derivative of the integral of 1 over t is just going to become, well, 1 over x. So the derivative of logarithm is 1 over x. So one of the things that's so nice about this approach is that we have learned that the logarithm function is differentiable and thus continuous for positive values of x. This is actually not trivial when you do the exponential approach, that even the fact that the exponential function, for example, is continuous is something that takes some effort to deduce. Remember that the old approach started with the exponential and then led to the logarithm, but I want to go in reverse. Here I'm going to begin with the logarithm, and I'm going to try to plug in the value of e. Now, notice what I'm doing here. I don't know what e is at this stage in this formula. This is a definition of e. My claim is that e is the number such that the integral from 1 up to e of 1 over t dt is equal to 1. So e is defined such that this integral is 1. Indeed, this integral at some point is less than 1, and at some point is more than 1. It must be 1 somewhere, and that place where it is 1, that is what I will define to be e. This is in contrast to perhaps other ways of defining e you may have seen in the past. For example, in Calculus 1, this limit definition came about by taking the derivative of a to the x by the limit definition of the derivative, then to assert that the derivative of e to the x was equal to e to the x itself. Well, that happened when the base value was equal to this particular limit, and that's where that came about. Nevertheless, the point is that we have this new definition of e, which comes about from this new definition of a logarithm function. Now, as you likely know, there are many different properties of the logarithm function, and one of those properties is that the logarithm of a product, logarithm of x times y, is the logarithm of x plus the logarithm of y. This is just one of many different log rules, and I'm going to show you the proof of this log rule, but the proofs for the other log rules are somewhat analogous, and I would encourage you to try working through them yourselves. Here's how this proof goes. Well, by definition of the logarithm function, this is just equal to the integral from 1 up to x times y of 1 over t dt. I'm going to take that integral from 1 up to x times y, and I'm going to break it up into actually two different integrals. The first integral is going to go from 1 all the way up to x, and the second goes from that value of x all the way to x times y. So the entire interval 1 to x times y is broken up into the 1 to x and the x to y. And indeed, one of the properties of integrals is that you can break up the domain. We call this additivity of domain. And indeed, a integral over a larger region can be broken up as the sum of two different integrals over a smaller region as long as they meet in the middle. It's 1 to x and then x to x times y. First of these integrals is just the definition of logarithm of x. But for the second, I want to apply a change of variables. So I'm going to apply the change of variables u is t divided by x. Then what happens if I use that change of variables? It gives me, well, logarithm of x for the first. And then for the second, well, if u is equal to t over x, and t is equal to x, then the lower limit of integration just becomes 1. And if t is equal to x times y for the upper limit of integration, then that's going to give you just the value of y. And likewise, the integrand is going to turn over to 1 over u du. What is this? This is just the same thing as the definition of the logarithm of y. So indeed, we managed to conclude that the logarithm of the product of x times y is just the logarithm of x plus the logarithm of y. Now, so far, we've only defined the logarithm function for positive values of x. So what should we do when you have negative values of x? And I'm going to begin by suggesting a substitution, which is u is absolute value of x. Now my x can be positive or negative, and my u is going to be positive. Then if I want to consider, for example, the derivative of logarithm of absolute value of x now, well, this is just a chain rule. It's the derivative of logarithm of u, and so you do, well, the derivative of logarithm of u, which is 1 over u. But by the chain rule, you multiply that by the derivative of u with respect to x. So what is that? Well, this is the graph of absolute value of x. And absolute value of x, its slope, its derivative, is either 1, when x is greater than 0, or negative 1, when x is less than 0, or it does not exist at x equal to 0 itself. So the way I capture this 1 or minus 1 for the slope is to write x over absolute value of x. Indeed, if x is positive like 7, this is just 7 over 7, which is 1, great. If x is negative like negative 7, this is negative 7 over positive 7, which is minus 1, again, great. So this derivative, of course, and then of course this derivative does not exist at the value of x equal to 0. Well, absolute value of x is the same thing as x squared. So this is x over x squared, which is the same thing as just, well, 1 divided by x. And again, valid only for x not equal to 0. So the logarithm of absolute value, this can be useful because if I want to find, for example, an antiderivative to 1 over x, well, since 1 over x can be positive or negative, it's helpful if you have an answer that has the same domain. So logarithm of absolute value of x is a better answer for an antiderivative to 1 over x because logarithm of absolute value of x is an antiderivative for all values of x except for x equal to 0, where logarithm of x is an antiderivative only on the restricted domain that x is greater than 0. So I hope you found this interesting new approach to the logarithm function where we define it in terms of an integral to be an interesting one that presents the same basic results that we know, like that the logarithm of a product is the sum of two logarithms, but with a bit of a different flair that allows for some easy computations, like, for example, that the logarithm function is differentiable by the fundamental theorem of calculus.